So welcome back again. And today let us welcome our young speaker, Vishwaajit. He is pursuing his BTech in computer science from IIT Mumbai, Bombay. And he is a member of the Krittika group at Astronomy Club IIT Bombay. Uh, so Vishwaajit, would you like to take the questions at the end or in between?
I would like some questions in between, like whenever there's a problem, because each step requires understanding of the previous step.
Okay, so the questions can be put in the chat box, or if you want, you can raise your hand and we'll unmute you.
Yeah,
Over to you, Vishu.
cool. Thank you. So I hope the links have been sent to you guys. Can you guys
Yes,
open the
they are
collab
put
link?
on the code. They are put on the classroom, so people can access it. Yes.
So if you open the collab link, let me
Just
just
1 minute.
screenshot
Maybe
it.
those who have not can take a minute and go to Google Classroom and get the links. Some of them would have not seen the message.
So is the screen share visible?
Yes.
Good. So I hope you can see this when you open the link. So if you guys haven't used Collab before, basically instead of running the code in your computer directly, and sometimes you might have to do some setup and all of that, instead of that we can run it directly online. So that is what this is. All of these code is still in Python only, but we're just going to use it directly on the internet. As you can see, like print just prints whatever you have put in. Okay, so as we know, like what we are trying to do right now is trying to see if some uh, we get some data from a telescope, and from the telescope it'll be data. The data will directly just be a sequence of images which you have taken given some time intervals. Now from that image we want to extract what we call as the light curve. I hope you would have, you know what that is. A light curve basically is a set of brightnesses with respect to time. And to extract that and find more information about it, we are going to use this module known as light curve. Uh, Very similar sounding name, but with a K. Uh, so most of the code has already been written by other people who do this. We are just going to be using that code and using it for what all we need. So to install the package, we write this pip install lightcurve, and how to run these cells are if you just hover over the cell, you'll see a play button. So you just run it, and it runs. It'll just take some time to connect. So, uh, just try running it and see if it works. It should. And here we are just installing our the light curve module that we need. That's what this is. Yeah, okay. So, but please just keep doing the steps that I do too. So, if there's any problem, just stop me or raise hands so I can tell. Fine. Now, from so there are two or three different ways you can get the light curve data. And to get this light curve, we have to first get the images right that the telescope has taken. One way is to directly take it from a big observatory database, or if you just mention the name of the star, so KAC means Kepler's catalog, and this is the star ID. So if you just search for it by using this method known as search target pixel file, and we can download it directly using Python itself. So what this line here does is, I am going to download the pixel file of this star. Any doubts? Okay. So once I downloaded the pixel file, it will be associated with this variable, and from this variable, I can get the light curve. So a simple 2 underscore light curve gets the light curve data into this variable LC. Now, what exactly is a light curve? A light curve is a set of brightnesses at some time intervals, right? So we can check what the time intervals at which we have taken the images by lc.time. Here we can see like at 14.1472 we have taken one, and 1472.13 we have taken one, 1472.15 we have taken one, till 1557.93. And the brightnesses have been 258643, 258660, so on. And we can just plot this as a graph. That is, this is our light curve just by doing lc.plot. So this is the plot, and we can see that the brightness is in flux. It is in flux because basically how a camera works is, when light hits the sensor of your camera, because light is energetic, it actually shoots out an electron from where the camera sensor is. Therefore, we can determine the amount of light which is hitting a sensor as number of electrons that is coming out per second. That is electron per second here. That is why the unit is electron per second here. And time, as you see, we started from 1472. 1472 is around here till 1557, which is around here. So, any questions till now as to what is? Oh, okay, what is quality bit mask? It is just basically when I'm downloading, we can download in different qualities, like how clear do I want the image to be. This hardest means it is there are different types of quality bit masks. Let me show you. I think it's here. So if you want like more information about all the things that I'm saying right now, the best way to do it is just search the module name. You'll get something known as light curve docs, which is basically everything about the documentation that you want. So here we go to this, and oh, sorry, and here we can search target pixel file. So this is what we searched, right? And here we have the quality bit mask. Here there are five different options. Either you can put none, default, hard, hardest, or int. And this is what they mean. So a cadence, you can think of it as just a photo, and none means none of the cadences would be ignored, and hard means we choose only good, like hardest means you remove all the cadences which have one or more flags that are raised. So there are different flags, in the sense is like this might have a problem or this might be a problem. Those are flags. And hardest removes all of it. How to download pixel data of the star? Yeah, so there are two different ways. I'll go to the first way in a bit. The second way is to directly just name the star name. So the star name here is KAC 8462852. So this is the star name. Quarter is basically somewhat with so this is taken from the Kepler telescope, and quarter basically is we divide the amount of time the telescope is looking in the sky in quarters. A quarter is basically a month. So a quarter equal to 16 means this is taken in the 16th quarter. Yeah, there is a threshold value linked to the bitmask stuff. Cadences. I think it is just the images. Cadence in light curve. Yeah, the rate at which the photometric observations are stored. It is the images that we are taking. Yeah. Any other questions?
Okay, just a question from where this file is getting uh, copied. I mean, this
Okay,
image
so
file,
yeah, so
this
actually,
KIC image file,
uh,
because we just copied that notebook and then it is able to open that. So my question is, where is that stored?
yeah, so light curve itself has, so this is what we are using. We are using the target pixel file, and it downloads it from, as far as I know, it, I, it downloads it from NASA's Kepler pipeline.
Okay, thank you.
Again, like that is one way. So light curve itself has this because people use this, but if we have, we can download our own the data separately too. So that is from this, there's this collection known as the masked observatory collection. Here we can directly go and search the catalogs and actually search for a specific star that we want to find, and we can download the light curve data from there. Okay. Any other questions? So, okay, about the bit mask. One second. Let me. I'll just go in order. Of what are we plotting the light curve of? No, of stars. So, light curve is basically the. Let's say you're shining. A star is when we are looking at a telescope and we are looking at a star. We are going to be taking images of the star, right? Now, from these images of the star, we can get how bright the star is. And this brightness with respect to the time, that is basically you're going to keep taking images. We are going to keep looking at a star for about a month, and we keep taking images of it, and from each image we calculate the brightness, and this brightness with respect to time is what we are plotting as a light curve. So we are actually plotting the light curve of the star, and from the light curve of the star, if we see some patterns, we say that okay, there is possibly an exoplanet there. Then bit mask. Okay, so when we are taking an image, let's say image of, let's say the sky, we see different stars, right? There's a lot of stars, but when we calculate the brightness, we want to only calculate brightness of one star.
You need to share that tab.
I'm just answering questions right now, so
Okay, okay.
So in a sense, like we just want to filter out the pixels which the star has. So for example, let's say I'm going a bit further just to show. So this is how an image would look. So this is the pixel row number, this is the pixel column number, this is the ID of the star, and these are the pixels we are going to consider while calculating our what we call as brightness. So cadence basically is at this time instant. So yeah, a bit mask basically this red lines are there, right? Those are the pixels are those are the only pixels I'm going to consider, and this is what I call as a bit mask, because I'm going to mask over the image saying I'm only considering these pixels. Can we use data from, I do not know what website it is, but if we get image, if we get the data in form of fits images, we can. What is BKJD? BKJD is Julian days. It's just uh, kind of a, it's something like BC or AD. It's just JD means Julian days, and we plot the data from scratch. What does the light curve do? Okay, so currently the data that we get are images like this. From this, we what light curve does is it looks at all the correct pixels, and this is a big problem because your image will be moving, so we can't just directly. So for every image, we have to find its bitmap and then get the data out, and from there we have to do the sum of all the pixels, and from the sum of pixels we have to plot it with time. So instead of us doing this manually for every image, we have this module light curve which does it for us. That's what this two light curve does. Here it is actually a like an image dot fits, and here it becomes a graph. Okay, then how do you know at what time to look at a particular star of interest? Okay, so here, how do we know? Okay, so here I searched for the target pixel file and downloaded it, right? So if I, for instance, not do this, and if I just search, oh wait, I think that was not the syntax. One second. Um, so there is a way where you can find, huh, search result. So something like this. We can search for the target pixel file and we can actually print the search result. And from the search results, we can see, so this is a star name, and we can see what telescope at what time has taken images of this. So currently this one, there's only one, but for others, there might be more. So here, let's say what I had to do was print pixel file, I think. See, here we are taking the image from Kepler from quarter 16. And if I had removed this, maybe there might be more. So this was taken at quarter 0, at quarter 4. We can take any of this data and upload it, but we can only download one data in the end. So we decided on 16 here, but you can choose to do it. Target pixel file, yes. How do we differentiate from in transit? hmm. I don't think we can just differentiate it from here directly, mostly because here a thing that exoplanets have is that it's periodic. So I'll show you some like once we are going a bit further, I'll show you how the light curve data of a exoplanet, like a star with an exoplanet, looks like. And Star spots actually do not show that pattern. So we cannot say that for certainty that there is an exoplanet there, but we can infer that there is most probably an exoplanet there. EXP time, that's exposure time, I think. So the camera was open for this much seconds. So
Okay. Shall I make a request here?
yeah,
Uh, because different students are going to be at different levels right now, though they know Python coding about exoplanet, basic thing they have learned, but they have not seen the light curves of
okay,
exoplanet. Is it okay if you can, go step by step, explain what is being done, or first explain the different light curves and then come back to the code?
okay, cool. So okay, so fine. Let's start here. Can everybody see? Is the whiteboard visible? It is, right?
Yes.
Okay. So let's say this is a star, and the star is like emitting light, and your telescope is here, and we are looking at the star. Now, I'm going to plot the amount of light that is hitting this telescope with respect to time. It would look constant. Is this fine? Like, because the star does not like, even if it brightens or dims, the amount of time that I'm looking at is like just 1 month, so it's very small time period. Now, if there was an exoplanet, what would happen is there's a planet and it's going to be moving around the sun, right? That means that when this exoplanet is in front of the sun here, the amount of light that comes directly into the telescope actually decreases for the time it is moving across its sun. So how that light curve would look is something like this. So there's a small dip and it continues until it comes back, and once it comes back there's another small dip, continues, a small dip, and it continues. And this is periodic, like the same structure will be repeated again and again, because the exoplanet orbiting its host star is periodic. So the amount of time it's going to spend in front of the sun and the amount of time it is going to be spending moving around the sun is constant. Therefore, these will happen in predictable patterns. Now, when we look at any star data that we get, this pattern is what we want to find. And if we find a pattern like this, we can say that there is possibly a exoplanet. So this is what we are trying to find. Now, every photo that we take from the telescope, it would be something like this, and there are multiple stars. But when we want to calculate the brightness of a singular star, that means that we only want to care something about around the star that we want. So this is what I call as a bit mask. So I am only going to be considering the data here. Therefore, I am masking everything that is around there. You can think of it as cropping it. Okay. So this is what we are trying to do. So we get these images, and from these images we are going to add up all the brightness values in every pixel, and then we are going to plot it across time. Time is in Julian days, JD. uh, was that fine?
Go back to the code and
Okay.
show the images and explain part of the images. What is noise part? What is the genuine data part? Those kind of things. And then, because what happens is the people who are fast learners, probably they may have a lot of queries in the code, but simultaneously there could be larger number of people who may just lag behind. So
Okay.
if you can.
Okay, so yeah, fine. I'll come back to the queries after the like once one time we have gone through the whole code. So it's not like it's going anywhere. But let us first go with this. So let me first find a pixel file for a star which I know has an exoplanet. So I know that this star has an exoplanet. So I'm just going to show you how the pixel file looks. So first I make it as a light curve and then I plot it. So as I had mentioned to you before, can you see these dips which are at a constant interval? So this is what we expect to see since we know that it has an exoplanet. Now, do you see this is very thick and fuzzy? That is because every time the light hits your sensor, there's a random probability that it shoots out an electron and it does not shoot out an electron. So this you call as a random error. So there are two types of error. One is random error, another is systematic error. Systematic error is something like, let's say you have a scale and the scale starts with 1 instead of 0. That means that every measurement you make will be offset by a value, right? So that is known as systematic error. And a random error is something you cannot do anything about. So it is something like, let's say you stop the clock. The human reaction speed is not constant. So sometimes you might stop right on time, sometimes you might stop before, sometimes you may stop after. So how you fix these random errors are you take a lot of measurements and you average it. So that is what we are going to do now in this. So you can see that it's very fuzzy, but I want a somewhat constant line. Because this is we are repeating this again and again. What we do is that, so this point, this point, this point, this point are all corresponding to the same event, right? That the star just the exoplanet just passes over the star. So what we do is we take an average. So what we're going to do is we are going to cut this into 10 pieces. I think there are 10 here. We are cutting this into 10 pieces and then we are taking an average of every point. That is what flatten does. Oh no, sorry. That is what folding does. What flatten does is, can you see that this line is actually a bit tilted? Uh, like this is supposed to be the straight line, but it's a bit tilted. This is because your telescope was actually moving to the right. Therefore, the light which was initially coming perpendicular now becomes a bit tilted. That means that the brightness also decreases. This
Could it
error we can,
could it could
sorry.
it be also because of the zenith angle change
Huh, yeah, it
or
can.
air mass? Huh.
So there are multiple reasons, but I think this one specifically was because the telescope was shifting to the right. But errors like this happen because this has taken over uh, a good amount of this, taken over 29 days, right? So there are always errors like this. So to fix that, what we do is we first flatten it. That is, set this straight here like this. We flatten it, then we plot it. Now, as I have told you before, we are taking these segments, right? These segments of one second. Let me just show it in the whiteboard. So our data is something like this. Sorry for my bad drawing. Since our data is something like this, we are going to take these segments, and what we are going to do is we are going to overlay on each other and take the average. Now to do this, we have to first find what the time period is, right? So the time period here corresponds to the time period of the exoplanet around its host star, because that is when the exoplanet will be at the same point again and again. Now, for that, what we do is we have something known as a periodogram. And what this periodogram does is it uses different methods to try and estimate what is possibly the periodogram. That's why it's called as periodogram. So we are using one method, that is BLS. There are other methods too.
Just a query here. So this particular periodogram is a function written specifically for this purpose.
Yeah,
So I mean, probably it could be using Fourier transform and then calculating something like that.
yeah, and that is one method. There are other methods, like there are multiple
Okay,
methods
fine.
that the periodogram can use. So here we are using something known as BLS power. I do not know the exact specifics of how it does it, but yeah, one of the methods that can be used is also Fourier transforms. So here we can see that the peak is somewhere around 3.5, and a nice way to, like, because the library we are using is made for stuff like this, they have in mind that we are going to use the maximum power period. So we use they have defined for us period at max power, and this is what the period is, 3.5 to 2. Now, what we do is we said we are going to take all of this in average, right? So that is similar to kind of cutting it here, and then folding it. That's why the name is fold here. We fold with period of 3.5 to 2. And what this T naught is what I want to be the center here, the center. Uh, I wanted the center to be somewhere along the dip. So from here I saw that 361 was near. Therefore I put T naught as 361 here. Here we can see that now it has become a much better, like, stronger line. It might look like the thickness is still the same, but that is because the scale has not changed. Here if you can see, like, the scale is different from here. Now, the next thing we do is, initially we averaged our time, but that was just 10. We can do a bit more of an average. That is, if it is something like this, that are data, I will take all the values here in this particular bin and average them and put them as the value for all of these points. So it would be, if your data was something like this, the average would become something like this. That way, like, every value in the bin will be equal and the noise would be suppressed. So that is what we call as a bin. And what bin size means is the size of which I'm going to consider for my average. So when I make my bin size as 10, we can see that the noise has decreased again. And if I had made it a bit more, let's say 20. Oh wait, I had to run all of these. We can see that it's a bit more better. But the problem with increasing bin size is that features which are close to the size of the bin size, that is, let's say, if I chosen my bin size such that it was fully inside this dip, then this feature would have been lost. Therefore, like, increasing the bin size, if you increase it too much, then we will miss the exoplanet. If we decrease it too much, there'll be too much noise. So we have to find a nice sweet spot. So till here we did all of them separately. That is like, first we did a flatten, then we did a fold, and then we did a bin. We can chain them together because it's Python. So we are removing nans basically means that I'm going to remove all the not a numbers, and then I'm going to flatten it, then I'm going to fold it, then I'm going to bin it, then I want to plot it. So I run this here, I get this. So okay, now back to like some basic questions. Is bin size somehow related to binary? No, it is just bin in the sense like, it is a common technique. How do I say? It's like a basket. So I'm going to say that everything in this from x to x plus 10 falls in this bin or a basket, and I'm going to take average of that bin. Yeah, bin size is something like sensitivity. How do you decide bin size? Basically, that depends on how much time it takes for the exoplanet to go about the its own host sun, because that is a feature we are searching for. What does folding do? Okay, once again, so we have random errors that come up. That is like, it might be because some cloud came. There are multiple reasons why random errors happen. One of it is just because of quantum mechanics. Just because light hits the sensor doesn't mean that it should register the light. Therefore, that itself is a source of inherent randomness. Therefore, there is no way you can escape random errors. How we try to fix this is, the only way to fix random errors is to take a lot of observations and average them out. Here, we do have a lot of observations of the same thing. So, this point basically corresponds to the star, the exoplanet all coming in front of the star, and this is leaving the star. And this happens multiple times over the course of the observation. Therefore, what we do is, we take this as our primary instance, and then we kind of split the whole time segment into uh, 10 or 15, how much ever there are, cuts. And once we have these cuts, we're going to say that, okay, now we have this, put this over this, and take the average. That is, this point and the corresponding point and the corresponding point and the corresponding point. I'm going to take all these values, average it, and plot it here. So that way, the random errors which came got averaged here. So if initially it was something like this, it would have tamed to something like this. The random errors would still be there, but the amount of random errors would be less. Now, but still this looks a bit fuzzy, as we have seen. This still looks a bit fuzzy here. So what we do is, we take a section in this time, and we say this is an average. We do something known as a rolling cut. So a bin here basically means that, okay, let's say this is my whole time, that is the period. Now I split this into, let's say, k boxes, and all these values I put them in these box. This values go into this box, this values go into this box, then I average them, and whatever box that I had here is the value I give. Whatever average that I had here is the value I give for the whole box. So this would look something like this. Now you can see that if the size of the bin becomes too huge, let's say it becomes this big, then this whole thing would have just been gone like this. So if the size of your bin should be smaller than the size, the amount of time the exoplanet spends in front of its host star, and it should also be big enough that the random noise also gets eliminated efficiently. That is the answer for it. That's how you decide bin size. If it's more massive or big planet, what change it creates? This dip here is there, right? That dip would be more. So let's say this is your sun. I am very sorry. This is your sun, and let's say this is exoplanet A, and this is an exoplanet B. The amount of light which comes is basically the area of the sun into the luminosity, and the amount of light this blocks would be the area of the exoplanet A2, A sun. So, in a sense, the amount of brightness that we get is AS minus A1 times L, and AS minus A2 times L. Therefore, if A2 is more than A1, that means the amount of light that comes to us is lesser, and that means this dip would be more. If the revolution period of a planet around the planet star is too long, uh, I don't think you can use this data. Uh, I think you cannot use this method then. Two periodogram. So what two periodogram does is that it gets the possible periods. Method basically means that I'm going to use this. For now, we can just ignore this, and we kind of have an estimate as to what possibly is the period here, right? So back to this code. Here we can see that this is around, let's say, 360 to 365. I see two peaks. That means the period should be surely less than 5. So that is what I use here. The period is possibly between 1 to 5. So A range basically creates a range of values. So what this basically does is it creates 1, 1.001, 1.002, so on till 4.009, 4.999 and 5. And from these values, it checks each value as to, is this possibly a period? Is this possibly a period? Is this possibly a period? And the way it checks is what this method is. And from here, we kind of just get, we just choose which one has the maximum power. What does remove nonce do? It removes not a number. Sometimes your data might be corrupted. So I'll show you some example of corrupted data. Yes, this is real-time data. Can we also calculate the radius of the orbit? Uh, we can calculate what is the ratio between the size of the sun, size of the star, and the size of what the radius of the orbit is. And probably with more data like the absolute luminosity and like temperature of the star, maybe we can calculate it, but I do not know. Okay, so I think those are the questions. Mass, that we can probably calculate with the temperature, I think. When I try to plot, this comes up. What? I cannot see. Second. uh, Maybe your, I think it might be collapsed. Can you check if your output is not collapsed? Is it mandatory to remove the points which is exceeding and less than? We can. We can remove it, and that is known as clipping. This also gives a method to clip. So I'll show that. I'll show some very bad data and I'll show you how to. So what you're seeing here is very good data. I'll show you how actual real life data, like worse real life data looks like. I'll just give it. The analogy is just that if you take an average of a random error, it goes away. In a sense, whenever let's say we want to check for how much speed a car is going, we check a different instance of time and then average it, right? So we do this. This is like general experimental process. Every time you make an observation, you make it multiple times and take the average of the observations. One second. Rise in the LC at a certain, that is just random errors. I see. Maybe 100 is good. I haven't tried experimenting with it as much. But do you see that it becomes a bit V shape? That means that we cannot, just because we have the data and we know that there's something, we cannot extract the data out of it. Averaging it, making the bin size too big also reduces the amount of data we. Okay. So, yeah, let me go back to the code now. I think that is enough. So, by the way, just randomly, if you are curious, this is a supernovae, and this is how a light curve for a supernovae looks. This is because this is when it actually went supernovae. That is why there's a sudden peaking of the brightness, and then it slowly decays, as you would expect for a supernovae. This was something that was cool, and I wanted to show. This was from EPIC. There are different catalogs. That's from one. Now, let us look at the pixel file of a star named Pi Mensae. So this was from mission tests. It was from sector 1, and the author was. So this is just like the data that I'm getting from here, and I'm going to download from default. That is like, I default means that cadences only severe quality issues will be ignored. Now we can ignore this for now. Now, if we look at the light curve plot, we can see how bad the data is, right? This does not look like something which has any exoplanets, as far as I can see. So the first thing we do is we create a threshold mask and we put a value for the threshold, and then I make it into a light curve, and then I'll show the plot. So instead of plotting directly, I see that there's a lot of lines here, right? That is because these are points and it tries to draw lines to form the points. It looks very cluttered. So what I do is I draw something known as a scatter plot. This S equal to 0.1 is basically the size of the point. So once we have done that, we can see a bit better. Like there's this dip here, there's this dip here, and this is dip here, and looks a bit periodic. And here I guess probably it went out of scope or something. So like the telescope probably moved away very fast. I do not know what the reason is, but this is bad data here. So we should not use these data. So the first thing I do is currently we can see that it's moving up and down a bit. It's not really straight. So first thing I do is flatten it. So once it's flattened, we can see the dips a bit better. Now, the first thing I do is the time here I know is between 1325 to 1350, something like that, right? 1325 to 1355. So we can see that this is around half the time. So what I do is I first split the time that I have into half the time. So here what this does is I'm starting from the zeroth instance to 5 times the length of the time divided by 10. The length of the time is basically number of images that I have. I am saying that I'm going to only use half of the images. That is only till here. Now if I put the scatter plot, you can see that it's a bit better. Now, but still we see that there are points here, there are dots here, there are dots everywhere. So the first thing you do is remove your outliers from here. We call this clipping because we kind of, it's something like clipping nails. We just clip the data. Now we can see that it's a bit more clearer that there's possibly an exoplanet. So from here, we first do our periodogram. We see that the time range can be between from like 1326 to 1336. So it is between 10. It's below 10. So I plotted. And you can see that the it looks to be somewhere around here 6.27. And so I just put the value and I fold it first. This is the folded value. And from after folding, I'm going to use binning. I'm going to bin it. So bin size 10 clearly looks to be a bad idea. One second, I forgot to run all of this.
Well, how did we get the time period? I didn't get that part.
We got the time period just by using the periodogram. So here, uh, as I said before, we first put our light curve data and we put a two periodogram. The method is BLS, and the period I have to first give a range as to what can possibly be the periods, right? So how I'm checking it is, we can see that I see a dip here, I see a dip here. Therefore, it should be between 1325, let's say, to 1335. So you can see that both the peaks are, both the dips are in between 1325 to 1335. Therefore, the time period, whatever it may be, should be less than 10. Therefore, it's obviously more than one and should be less than 10. And here, I'm just going to search for it.
Okay,
And
yeah.
after that, I just do period at max power and get the value.
Thank you, sir.
Sure. So here we have the folded values, and let me increase the bin size to something more, say 30. That's a bit better. Yes. Yeah, so from here you can see that there is an exoplanet for this. Yeah. So till now we have been using data which we got directly from here. Now let me just, okay, before I go to the next step, is there any doubts on what I have did till now? So like, what is a spike? So just, I have no idea, but I think there is some significance to it. So what is folding? So okay, so Okay, let us change the experiment a bit. Let's say I have a pendulum and I want to find what's the time period of the pendulum. How do I do this? Initially, I just start the pendulum and kind of eyeball it. Be like, okay, one swing has gotten over. I start the clock. I stop the clock right now. But in reality, when we do this experiment, what we do is we let the pendulum actually swing 10 times, and then we stop our clock, and then we divide the value by 10. This is because we have our innate error, like we cannot exactly stop our stopwatch when the pendulum is at its peak, and we cannot also exactly start the stopwatch when we are going to leave it. That is the problem we have. And how we are fixing is that error only happens once, and because it is random, if I had taken the experiment 10 times and averaged it, we decrease the error. Similar is what we do in folding. We have the observation and we see the dip 10 times. So what we do is we split it into 10 different experiments and then just correlate every point with every other point in these 10 experiments and then average them. In a sense, if I had drawn 10 points on paper, I'm folding this paper.
Sir, I have one question, sir.
Yeah, go on.
Sir, when we bin the graph and we get the output graph, the unit of x-axis is showing in terms of phase and Julian days. What does that mean, sir? What is the phase in terms of Julian days mean, sir?
Okay. So,
This unit, sir. Phase in terms of JD.
okay, so if I had to, hmm, okay. So, see here. Here we said, like before this, we used t naught equal to some value, right?
Yes, sir.
Uh, that value will be now put as the zero of this. And since we know it's a periodic thing, right? Because we found a period for it and then only we folded it. Since we know it's a periodic thing, usually what we say, like what from the center at 2 seconds later something happened, or in terms of SHM, like in SHM we have that sine theta plus phi, right? That phase that is similar to what we are using here. We are saying that from the center after 2 days, this is the value that I get. From the center after, let's say, what is this, 0.2 days, I have the peak dip. And the zero could mean anything. The zero
The
is
negative
either,
sign means before that period come before the star like this, sir.
sorry, can you repeat?
So if the 2 means from the center after 2 days, the position of the planet is like that. So the negative 2 means before it interfering the observer and the star, it was in that position like that, sir.
This is not percent, this is flux. But yeah, yes, that is what it is. The brightness 2 days before the dip is this much. The brightness 2 days after the dip is this much. Yeah.
Actually, by
Okay, sir.
changing that period, which is that 6.276,
Yeah, yeah.
you are changing the folding rate, and therefore the noise may not get cancelled, right?
Yeah. In fact, it would be
So
bad. Like
instead
I
of
can show it
doing
how it looks.
if you take 6.2, then also it will change.
Yeah. Let's say I took 3.2. See, it's just gone. Actually, this was corresponding to the div, but it got moved. If I had instead did 6.2 itself, let's say, uh, it is still there, but we can see that it's not effective. That is because I did not find the period correctly. That is why we use period at max power here instead of just eyeballing and saying, okay, this looks to be around 6.1. So I can just go with it. That is why we do the period at max power. Uh, Threshold mask. I think it is a bit advanced, but threshold mask we can just kind of experiment with it and see what more parameters can you find. With the dip, we get more data, but I don't know. I'm sorry. So yeah, for the the create threshold mask, you can check the documentation. Like you can just go to light curve docs and go to like whichever one. So all the functions here are here. Like every function that you need, what it does is here. You can just go in here and check like what exactly it does. Having fits file. Yeah, it can. You can just a fits file is enough, and like the aperture mask basically saying that okay, just take these values is enough. Okay, now now we from here we have till now we have only been using like we're directly down. We're just mentioning the name here, and we're just mentioning the name here and the mission and downloading it directly, right? Another way to do this is actually go into this website, which is known as the masked catalogs. And what we do is now here we are going to search for stars. So we do something known as an advanced search. Now in this, we can here let's say I want to find some stars. So this has all the stars that have been found from certain from this catalog. Let's say I want something which is at these are parameters. So from here I can get something like I want only stars which are close to me. Let's say between 1 to 353 pascals, I think. So let's say 1 to 10 pascals. This is my first parameter, let's say. And then let's say that is it's between 1 to 10. I think it's in light years away from us. Then there are more parameters, something like the stellar mass should be only around 1 to 10 solar masses, maybe. Like, let's say something like this. And no, this is too high. So 1, 2. Here we have 239 records. And then we can find like the effective temperature that is there. 1, 2, let's say 3 times. Now, once I have found these records, I can always search. And once I search, I get these values. So, like, these are the IDs of the stars. And here we can see, like, the different stars which are there. Uh, Here we want to get the source of type as something known as test CTL because that is the stars that we usually have the data for. And let's say, for example, let me go back and let me do a search which is like hide all, and I just want to find for distances. I'm just trying to show you like to download one of the data. 1 to 10. So okay, so like let's say we just have this star, and let's say I want to search for this star. So copy this, and then I'm going to search with object name, and then I put TIC because it's a TIC ID. and search the name. So this is currently searching. A bit slow. But yeah. Yeah. Once we see, here we see that we have data, and this means that there is like of data. So one thing we can do is we want to download these data projects, and usually this is like a better UI. So once we click the save button, we click this link and it takes you here. And here we can either use the target name, which we have been using here, or like the RA deck data of it. And from the resolution, we can download this FFI cutout, which is basically the image data that we have. So here we can select which sector, which author, and what is the size you want. So yeah, and from there, the data that you like, the image that you downloaded, we can add as a file here. We can upload the file here, and once you have uploaded the file, we can link we can link the file here, and from there all we do is what we have done till now, just flatten, two periodogram, fold, bin. Yeah, and then we can search if it has an exoplanet. So yeah, this is the second way of getting your data, that is directly go into the observate like masked catalogs. We can go to the masked catalogs. We first click mission test CTL. CTL basically means candidate list. Basically, these are stars which possibly have exoplanets, but they haven't checked it. So it is just open. So we can go to advanced search. We can filter as to what we want. And once we are done with the filter and we have decided that, okay, this is a star I want to check for, I can go here, click this, and go to my target and download the image and then do all the data processing I've done till now. Cool. So yeah, that wraps up what I wanted to show. Is there any doubts?
Sir, I have one question.
Yeah.
So if a star has two planets with almost same orbital period, and we perform these calculations we do now, like flattening the curve and updating the maximum period. So if since both stars having same time period, what if two peaks collide at the same time period repeatedly, sir? So how can we sort out that period and we can find this planet is this and this planet is this?
Uh,
First thing, what is meant by two planets having same periods? Are they moving in the same orbit?
No, sir, not like that. Not exactly same period. What I'm asking is because in the case of Kepler system, there are two planets with one has 1.5 Julian days and another one has I think two. I know the exact value 2.2 Julian days. So if we sort a graph, like it would be like exactly the same, no, sir. Like it there's no much
You
of a difference.
look at the percentage. Look at the percentage. 1.5 and 2.2. The number looks very small. Look at the percentage.
there is a very huge difference.
The size of planet can differ, so the width of the depth can be different. even though the rotation revolution period is same.
So that is a different thing. But first of all, having two planets almost with the same period itself is very difficult. Generally, if you look at this TTS board law observed here in the solar system, similar law is also observed in multiplanetary systems. That is what is being checked by now. So that's of course meeting, but most importantly, you can't have something like that. Generally, they go in geometrical ratio.
Okay, sir.
Can we go for a quick small poll? And then, of course, we can take more questions. So I'll just launch a small quick poll for 5 minutes. Everybody answer this. You're sharing the screen, sir.
Sir, have we launched the correct poll?
I realize that just now, but let the poll get completed, then we'll go for the new poll. Sorry for this confusion. But everybody do answer this. I mean, you had answered this, but please answer this again. I will launch the fresh poll, but please answer all this again. Okay, I'm ending this poll and I'll put the fresh poll. Shubham, are you there?
Yes, sir.
Everybody please answer this poll. I will end the poll in another 15 seconds. Okay, ending. Yeah. Yeah. Thank you, participant. Vishwajit, you may continue.
Yes. Okay. I
There's a
think.
raised hand. I think somebody has a question.
Okay. Just.
Hello, sir. Good evening. Hello.
Yeah. Yeah.
Okay. In the dip, in the light curve, we see a dip, right?
Yes.
So in the dip, there are two things. One is the length of the dip, and other is the broadness of the dip. So
Yeah.
what exactly the broadness and the length will tell you about a planet?
So the broadness will tell you the ratio of the radius of your star with
Okay.
the ratio of the radius of the orbit of the planet.
Okay.
And the dip tells you something about the radius of the exoplanet
Okay.
with
Thank you.
respect to the radius of the star.
Okay. Thank you.
So I'll just show the downloading the data part again since people were asking. So first we go to let me just start from scratch. First we go to we open this link, we go to massed catalogs, and then we search for this mission test CTL, and then we go to this advanced search. We put the filters that we need. Here I've just put a distance filter, and then we click search. And once we click search, we get this all of these. And from here we have TAC IDs. So like these are basically the names of the stars. Let's say I take this star, then I first click massed observations with object name because I'm going to use the ID, and then I enter the name. Since I am using a TAC ID, I should start with TAC, and then I search, and this takes a bit of time. And once I searched, I can see that there is data here. So one way is to directly just try to download this, but a better way is to directly just go into test cut. And here I can either use RA deck here, that is show this these values RA and deck here, or I can use target name, which is PIC, and then I can resolve it. And once I have it resolved, I can see which sector I want, and then I can download the cutout. Yes. So is that fine for the downloading the data? There's just different ways to say. I think I think you should Google it. It's binning. Uh, what I did for folding is similar to what we do for binning. So, example for somewhere else that we use binning is, let's say we are finding the velocity of a car. Let's say we don't actually find the velocity at every single instance of the car, right? What we do is we look at time intervals of 1 second, and we see, okay, this has moved this far, therefore the velocity in that 1 second is the distance it moved in that second divided by 1, and the next second will be how much it moved in the second divided by 1. Similarly, what we do here is we have time instances of, let's say 10 10 brightness at the first second, and 1.01 it was 11, and then 1.02 was 9, something like that. What we say is I am going to look at the whole of 1 to 1.10, that is 10 time instances, and then I'm going to take the average of everything. That is, let's say for this it's 10. That means at 1.1 it was 10, at 1.0 it was 10, at 1.01 it was 10, at 1.02 it is 10, so until 1.10 it is 10. That is what I mean by pinning. Okay, any other questions?
Any other questions? Yes, you can unmute and ask, or we can end here. Right. There are one or two questions in the chat box. So question is, binning and folding are the two different ways of averaging. So this is the question. So you answer yes. So I think stop here, and let us take this opportunity to thank Vishwajit for the wonderful lecture. He has shown us how we can go to a particular site, download the data, and using the light curve and using different functions like flattening, folding, binning, and so on to get useful data of the exoplanets uh, using Python programming. Thank you, Vishwadip and Mahesh. Stop here.
Yes. Thank you, Vishwajit. We will end the session here.